Our next speaker is Erika Rader, who will be speaking on modern field tools to investigate geologic environments. I guess there's a new title now.
So I will be kind of presenting a bit about the volcano side of some of the questions that we might be able to answer with using modern field tools as well as the traditional field skills. And this comes from a bunch of projects that I've worked on, observations and discussions with people from basalt, finesse, feldspar, and ice crystal teams. Next slide, please. So what I hope to convince you of by the end of this talk is that we can augment our science using these portable tools, and with the improved communications, streaming data back to various different specialists. I think I'll show you that we can answer more questions than we could if we just had geologists, well-trained geologists on ground in the field. But I do want to say that I completely agree that geological field training is super valuable and should definitely and cannot be replaced by these instruments. Okay, next slide, please. Oh, good. So the tools that my group has been using includes the X-ray fluorescence spectrometer on the left, which does bulk composition of rock, the visible near infrared spectrometer in the middle, which does mineralogical type characterizations, and then the laser-induced breakdown spectroscopy or spectrometer on the right, which does geochemical as well, but sort of depending on what exactly the laser hits, it might be more of a mineralogical composition or a bulk composition. Next slide. The two goals that we had were to, in all of these projects, was to figure out if we could document as much about the geological environment as possible without slowing down people, and then also to see if these instruments could augment the types of analyses that we get from thin sections, which is a specific tool in geology to study rocks. Next slide. And the purpose for this was obviously there's only so much a team in the field can do. So having outsourcing some of that documentation and descriptions to people who aren't necessarily there is really important. And then for the thin sections, those are a really basic fundamental part of understanding the rocks, but they take a lot of effort to make, since you have to collect the rock and then bring it back to Earth theoretically and process it, turn it into a thin section before you can get any information. So if we can figure out a way to use these tools to get around that process, then that'll really save a lot of time. Next slide. So the environmental part of this is that volcanoes can do erupt into a whole bunch of different environments, and so they can be they'll be interacting with different environments, and they can be environmental indicators as long as you can see all of the different parts of them. So with thin sections, you get to see the crystal size and the crystal shape, for example, which is really affected by how quickly something cooled. Next slide. This is one example, not the best necessarily for the South Pole, but one example is that there have been different cooling environments proposed on the moon. So these are the Marius Hill domes on the right, and they've been proposed as potentially rootless cones, which is a volcanic feature that forms when lava interacts with water. There's going to be a much faster cooling rate for those types of deposits, theoretically, than a volcano that did not interact with water. But as you can see in the bottom left-hand corner, this is an image of the San Francisco volcanic field in Arizona, and those cones are distributed randomly, similar to the image on the right of the Marius Hills. So basically, we're going to need more information from these rocks to be able to really narrow down where they came from or what environment they erupted into, or their petrogenesis, for example. And this is even more true if we're talking about breccias, where we have basically no idea where these things came from. We still might be able to get information about what environment they were erupted into or erupted through using thin section type analyses. Next slide, please. So this is just, again, an example. This is sort of one question that this type of utilization of instruments can help with. The theory behind this, you have bigger crystals on the left here and smaller crystals on the right, and those are preserved in environments that are either cooled slowly, allowing the crystals to grow, or cooled quickly, preventing the crystals from growing. And two examples of where those types of environments might be: on the left, a place where there's a ton of lava erupting in sort of a contained environment. It's extremely hot. Things aren't going to cool very quickly. And then on the right side, an environment where lava is flowing into water here, it's going to cool much faster. And you should be able to see that in the thin sections. That graph in the middle is just the quantitative data from the crystals. And the thin sections, you can see that as the cooling rate increases to the right, the bigger crystals on the top decrease and the number of crystals that are small increases. So next slide, please. So this is just an example again of one question that these tools can be helpful for. So the question that we've been talking about with making geologic observations, can we get all of this data without bogging down the crew? Some of the obviously in-field observations are extremely important and provide the context for everything. Having one person, recording this in the field while everybody kind of makes observations is what we've done in the low-tech model. The high-tech model, having data streaming to a room full of people who are tagging and annotating and describing and making that data available. This really is important. It takes the burden off of the crew out there, reduces the stress that they're going to miss something or make a mistake and not capture something. So having things documented, streaming is a really great idea, and it allows for a lot more people to contribute to the descriptive process. Next slide, please. Getting back to the how can we get around thin section question, this is kind of a lot of information on this slide, but this is just to illustrate that how we have gone out and zapped a bunch of rocks and then done the exact same analyses that we do to get data about what these textures are and what the cooling environments are. And we can see that from the thin sections, it's very easy to tell that these rocks had different cooling environments. There's different sizes, different shapes, different types of crystals. And then on the left side, we have spectral data. Collecting that spectra took 15, 30 seconds. Getting the image on the right took 6 months with delays and COVID and all the things. So obviously getting the spectra is a lot easier to do and can fill in gaps. If we can only get 1 or 2 samples, but we can get 100 spectra, that's great. So next slide. This just kind of reiterates that even in the easy times of Earth, atmosphere, and gravity and all of that, it can take a while to hammer out the rock that you need. You can get 5 to 10 analyses done with these instruments in that time. And if you have one person who's really well trained in geology and the context of things, they can direct the others who don't need as much training in that to be the instrument, the people who are running the instruments. And that way you can kind of have people who take their training time and utilize that in other ways that are really important for the mission and maybe not need quite as much geological training, but can still gather a ton of data. Next slide. This might not be as relevant considering the constraints that I was not super aware of about bringing stuff back to the lander. But another great thing about these instruments that are handheld is that if you grab a couple of rocks on your way out and then you just want to analyze them and then leave them on the surface of the moon, that's a way to maybe say, oh, we have 50 rocks that are great, we can only take back 30. Well, let's analyze these 20 and then leave them here. And that's another really useful part of these instruments potentially. Next slide. And then I also want to reiterate that having the hyperspectral and gigapan images of the rocks is another great way to pretty quickly get a ton of data that can then be analyzed by specialists or whoever back on Earth, allowing a lot more science to be done eventually and not necessarily in the moment. Next slide. So this, yeah, basically this is just again saying we took these spectra, we can make these end members based on the in situ spectra, try to utilize satellite data to build a picture of what the geology is doing from just a couple of points. And we're going to go this summer and test this map out to see if these spectral patterns that we've identified mean what we think they mean with regards to the eruptive environment of this particular lava flow, thanks to these instruments. Next slide. So yeah, in conclusion, I think that understanding what question you're answering can really allow you to target what you're using your instruments for. They are easy to use and really quick. So as long as you're not dedicating all of your time to just using those instruments, they can really augment the kinds of training that you have, or the kinds of observations that well-trained geological field folks can do. Once the geological training can help you target what things you should be putting your instruments up against, then that can then allow the instruments to help you high grade sampling if you need to have specific characteristics. So for example, in the studies that I've done, having really glassy rocks or really rocks with a lot of olivine or rocks with a lot of plagioclase for kind of petrologic studies. I don't know if this is possible at all, but I thought, hey, why not? Having an auto sampler where if you bring rocks back and then these portable tools can be run overnight in some way, then that can not have any burden or a smaller burden on the crew while they're sleeping. And then utilizing a crowdsourced style of note-taking, image tagging, and environmental interpretation, having that streaming data is going to be really helpful and really important, and a lot more observations can be made if we kind of distribute that work throughout the community. Okay, thanks very much.